Okay, all right. So let's continue discussion of p-n junction diode. Maybe we stopped the mechanical valve analogy, but I'm going to go back a couple of slides and talk about minority and majority charge carriers. Let's see. Okay. All right. So we looked at p-type semiconductors, n-type semiconductors, and then we created a p-n junction diode using p and n-type materials, right? So when we bring them in close proximity, or when we fabricate them with close proximity, at the junction of the p and n-type material, the electrons and the holes recombine. Recombination takes place, takes out two of the charge carriers. Hence, there's a region right there at the junction that's devoid of all charge carriers or all charges. Hence the name depletion region. Now, in a p-type material and an n-type material, we already have intrinsic carriers that are present, right? Thermal effects. At room temperature, a semiconductor material will always have certain amount of free charge carriers. They are not so large in number as to classify them as conductors, right? But they are not as low as what we have in insulators and semiconductors. So when you create excess of charge carriers from external impurities, you have both kinds of charge carriers that are present in a material. So in a p-type semiconductor, you have intrinsic charge carriers that are holes and electrons. Plus, you have excess positive charges that are introduced because of the column 3 elements. Okay, so there are intrinsic charge carriers that are present in the material itself because of thermal effects. At room temperature, you always have free electrons and holes. Plus, we are introducing external impurities. So in a p-type material, you have excess of holes, and in an n-type material, you have an excess of electrons. But both of them still have the intrinsic charge carriers. It means that in the end result, we have p and n-type, both p and n-type materials have both electrons as well as holes available to carry the charges. But because of the large volume or the large dosage that is introduced into the material, we have excess of holes in p-type and excess of electrons in the n-type material. But they both also have holes as well as electrons. So the large number of, write it either ways, let's write it here. So in a p-type material, there is a large number of holes that is due to the external doping. Plus intrinsic, the thermal effects, you also have holes. And because these are larger number, these are known as the majority carriers. Both holes and electrons carry the charges, hence they are known as charge carriers. In a p-type material, holes are referred to as majority carriers, and electrons are labeled as minority carriers. So intrinsically, because of thermal effects, you have electrons and holes in a p-type material, and then you have excess of holes introduced from external impurity doping. So extrinsic semiconductor, holes are large in number, hence majority carriers. Electrons are low in number, hence they are minority carriers. And when we get to an n-type material, it's flipped. In an n-type material, electrons are introduced due to the external doping. Hence, electrons are the majority carriers. And holes or the minority carriers. Okay. And they're both free to move about in a lattice material. So energy can be transferred due to the flow of either electrons and holes or both electrons and holes. So in a diode, current flows due to the effects of both electrons as well as holes. Hence, it is a bipolar device, which when we get to a BJT is implied in the name itself, a bipolar junction transistor. Okay, the bipolar in BJT stands for the effects of both holes as well as electrons, both positive charges and negative charges. Okay, both kinds of charge carriers are responsible for current flow in these devices. That's where the term bipolar comes from. Okay. Any questions? We already looked at the mechanical valve analogy. Let's look at the VI characteristic. So we plot the values for current as a function of voltage. We obtain what is known as the VI characteristic, also known as the IV characteristic, current as a function of voltage. For a resistor, capacitor, or inductor, it's basically a straight line. As the voltage is increased, the current increases. If the voltage decreases, the current decreases, right? So that is true for both, for all three: resistor, capacitor, and inductor. Voltage is a function of the, current as a function of the voltage. For a diode, not so. And this I'm just zooming into. So voltage on the x-axis, current on the y-axis. If I plot the current for a diode as a function of the diode voltage, it's going to look something like this. It's going to remain a 0 for a certain period of time for certain values. And then after that, it's going to increase. This value right here, and this is exaggerated, of course. The slope is also exaggerated just to show you the effects. This is known as the diode voltage that is required to turn it on. And for silicon, it is between 0.6 and 0.7 volts. For germanium, it is 0.2, 0.3 volts. Let's put it here. So this is germanium. This is silicon. And this is 0 amps. This voltage, also known as the knee voltage or the diode turn on voltage, is basically the minimum voltage that is required to overcome the width of that junction. Okay, the junction barrier, the depletion region junction barrier, prevents any current from flowing until that voltage is applied. Okay, so for a silicon diode, doesn't matter how you create the diode, meaning the dimensions do not matter, the doping does not matter. It always is 0.6 to 0.7 volts. And that amount of voltage is required in the forward bias to turn the diode on, meaning to permit the flow of current. That is basically, in terms of the device physics, there's the depletion region. The depletion region needs to be overcome. The width of the depletion region needs to be overcome. And that always is 0.6 to 0.7 volts. So this voltage is known as the knee voltage or turn on voltage. Diode turn on voltage or the knee voltage. And so this is the forward bias VI characteristic. Typically, you would just see something like this, a line going straight up. Okay. But the point is that it is non-linear. So if you look at the characteristics, even if you keep increasing the voltage, it remains zero for a long time. And after it crosses or it turns on, current increases rapidly, meaning for a small increase in voltage along the x-axis, the current increases by a large number. Okay. From that point on, it is at least linear. Overall, it is considered to be non-linear, but the portion after it turns on is typically linear. If you take a look at the reverse bias, it's very different. Reverse bias, you have the depletion region. And we talked about this here, where the positively charged holes and the negatively charged electrons are attracted by the reverse bias voltage that is being applied externally, and hence they are pulled away from the junction. So the depletion region increases in width. And because of that, there is no current flow. The only current flow that takes place is due to the intrinsic minority charge carriers. So in a p-type material, you have electrons that are the minority charge carriers. In an n-type material, it is the holes. So those are still going to cross over the junction. But they are so small in number, they are so low in number, that the resulting current is also very, very low. So the value of that current is typically in the nanoamps or the femtoamps range, 10 raised to minus 9, 10 raised to minus 12, 10 raised to minus 15. It is so low that we typically are not able to measure it in the lab. Okay. It is also known as the saturation current or the reverse saturation current. And so you see that here. The value is so low that it cannot be measured. And it's known as the saturation current, typically referred to as IS. It is very, very low, typically in the nanoamps. So this is exaggerated. This distance is exaggerated. Okay. All right. So if you forward bias a diode and you cross 0.6 to 0.7 volts, current is allowed to flow through. Large amount of current flows through for a small increase in voltage. In reverse bias, it's going to remain zero for a long time. You keep increasing the voltage, 10 volts, 20 volts, 25, 30, 40, 50. After a while, sufficient energy is imparted into the carriers that the depletion region width does not matter. They acquire enough energy that they're going to cross over the junction, resulting in a large current flowing through the junction. And so that is known as the breakdown. The junction breaks down because so much energy is being imparted to the carriers that they're able to acquire that energy and are now free to move around. They cross over the junction and current starts flowing in the opposite direction, which is indicated right here. So the junction breaks down, also known as the breakdown region right here. And this occurs in reverse bias, hence known as the reverse breakdown. And there are two mechanisms for this reverse breakdown. First one is known as Zener. The second one is known as avalanche. So let's talk about that. So here, of course, is the depletion region that is expanding. And here junction breaks down. Okay. And for a very small increase in voltage, a very large increase in current takes place in the opposite direction. Okay. So large current is flowing through. And of course, it's in the negative direction. The voltage polarity and the current direction for a diode is always taken as going from anode to the cathode. Anode is always positive, cathode is always negative. Okay, so if diode voltage, when somebody states diode voltage is 0.6 or diode voltage is -5, anode is always positive, cathode is always negative. So if you're measuring in the lab, you would take your meter, negative would be connected to the anode, cathode, and positive connected to the anode. That's always your reference. Okay, so always keep that in mind. So if you simply read a spec sheet or somebody's report, it says they measured -1 milliamp flowing through the diode. If it says -1 amp for a diode current, that means the meter was connected with the anode as positive reference, cathode as negative. It's going down this way as the arrow suggests in the illustration. Okay. And if it says minus, meaning its actual current is flowing in the opposite direction. So always keep that in mind. Okay, so reverse breakdown occurs because of two mechanisms, Zener and avalanche. Zener breakdown occurs because of very heavy doping, meaning the device is fabricated with high dosage of impurities. Okay, and that occurs during the fabrication or manufacturing process. So diodes, some specific diodes are created to operate only in the reverse bias. And the reason is because we want to take advantage of that near constant voltage that occurs right here. So in the reverse breakdown, when you have a Zener diode, the voltage across the diode remains constant once it reaches a certain threshold. The threshold depends on the doping during the manufacturing process. Okay. So as you can see in the image here, in the illustration in the graph, is that the voltage is almost constant, flat line, whereas the current has increased by a large number. And we use this property of a diode in reverse bias to create Zener diodes. Okay. It holds the voltage constant while permitting a large amount of current to flow through itself. So Zener occurs because of heavily doped PN junctions. Okay. And this is typically less than 6 volts. Okay. The Zener effect is typically seen for less than 6 volts. An avalanche occurs because of impact ionization process. It's typically greater than 6 volts. And what happens in impact ionization is you have these charge carriers that are present in the structure. Now you're increasing the voltage, and because you're increasing the voltage, meaning you're applying an external electric field. So externally, we're imparting some energy to these charge carriers. And they acquire so much energy that they are now free to move around in the lattice structure. And when that happens, they're moving randomly. Okay. They're moving in the direction of the field, of course, but they're moving randomly. And because of the large amount of carriers that are acquiring this energy, they're going to go collide into other atoms. So one free charge carrier is going to collide with an atom. It releases one or two or even more free charge carriers. Sorry, not free charge carriers. It releases more charge carriers. That one turns into two. Those two in turn acquire enough energy, and they're going to go ahead and collide into further more atoms. That turns into 4, 5, 6. So 1 turns into 2, turns into 4, 8, 16, and so on and so forth. And so it causes an avalanche effect due to impact. Because they're colliding with atoms, which are losing electrons, creating more ionized atoms, hence the term impact ionization. And because it's an avalanche effect, because it kind of avalanche effect, hence the effect is also known as, the term is so called avalanche effect due to impact ionization. So more and more and more charge carriers are generated because of the high levels of energy that are being applied externally. Okay. So the two breakdowns, one is Zener, that occurs because of heavy doping, less than 6 volts, and larger than 6 volts is due to the impact ionization process. But generally speaking, nowadays, both of them are like mixed up. If breakdown occurs in the reverse bias, whether it occurs due to Zener or whether it occurs due to avalanche effect, they're all commonly referred to as Zener effect or Zener breakdown. But technically, Zener is separate, avalanche breakdown is separate. Okay, so you keep that in mind. So if you read or hear somebody talking about Zener breakdown, it might generically just be like operating in reverse bias, but technically it could be two different mechanisms. Okay. And these, of course, we will look at separately under the section of Zener diodes, right? So let's see, next is load line analysis. It's not enough time to get into load line analysis. So I think we'll stop here and we'll end class here today. If you have any questions, you let me know. Today, I'm going to be in my office for a bit after like 2:25, 2:30. But then after 3 o'clock, I'm going over to a different lab in a building. So if you need to see me, come between 2:30 and 3. If you have any questions, just send me an email and I'll be happy to answer those.